Tonight, we're going to talk about one of the quietest and most persistent mysteries in all of science. Why, in a universe this old and this large, have we found no sign of anyone else? Before we get into it, if this is the kind of question that keeps you up at night, take a second to like the video or subscribe. It's a small thing, and it helps this channel reach more people who think about exactly these kinds of questions. Now, let's begin. Here's what most people assume when they think about this question. They assume we've been listening for alien signals for a while, that we haven't heard anything yet, and that this is slightly disappointing but not necessarily surprising. Space is big. Aliens might not be using radio. We haven't been looking that long. The universe is patient. Maybe we just need more time. That's a reasonable thing to think if you haven't looked closely at the numbers. But when you do look closely at the numbers, the silence stops feeling like a minor mystery and starts feeling like something that genuinely needs explaining. Because by any honest calculation, we should have heard something by now. We should have seen something, and we haven't. And the reasons that have been proposed for why that might be the case range from deeply reassuring to quietly unsettling to, in a few cases, the kind of thing you sit with for a while afterward. By the end of tonight, you're going to understand why the silence isn't just an absence of information. It's information, and it points somewhere specific. Let's start with the scale of the problem. The Milky Way galaxy is about 100,000 light-years across. 1 light-year is the distance light travels in a single year, moving at about 186,000 miles per second. That's fast enough to circle the Earth 7.5 times in a single second. Over a full year, light covers about 5.9 trillion miles. So 100,000 light-years is about 590 quadrillion miles, which is a 590 followed by 15 zeros. If you laid that many paperclips end to end, you'd have a chain roughly 1,000 times longer than the distance from Earth to the nearest star. The Milky Way contains somewhere between 200 and 400 billion stars. That range reflects genuine scientific uncertainty, not imprecision. Counting stars in your own galaxy is like trying to count people in a city by walking through the city with a blindfold on. You're embedded in what you're trying to measure, which makes it hard, but even the low end of the estimate, 200 billion, means something significant. Of those hundreds of billions of stars, we now know that most have planets. Not some, most. The Kepler Space Telescope, which ran from 2009 to 2018, stared at a small patch of sky containing about 150,000 stars and confirmed thousands of planets orbiting them. When astronomers extrapolated from those results to the full galaxy, they estimated there are at least as many planets in the Milky Way as there are stars, probably more. So we're talking about at least 200 billion planets just in our galaxy. Of those planets, a significant fraction orbit in what's called the habitable zone, the range of distances from a star where liquid water could exist on a planet's surface. Water is important because, as far as we know, liquid water is required for the kind of chemistry that produces life. We don't know if that's a fundamental constraint or just a reflection of how life works here on Earth, but it's the best criterion we have. By current estimates, roughly 20 to 40% of Sun-like stars have at least one planet in the habitable zone. Applied to the full galaxy, that's tens of billions of potentially habitable planets. And the Milky Way is one of roughly 2 trillion galaxies in the observable universe. So when we ask, why haven't we found aliens? We're not asking why we haven't found life in some small sample of a mostly empty universe. We're asking why there's no sign of life anywhere in a universe that contains more potentially habitable planets than there are grains of sand on every beach on Earth, combined many times over. That's a real question, and the silence is a real answer that requires a real explanation. Here's the version of this that most crystallizes the problem. The Milky Way is about 13 billion years old. Our Sun formed about 4.6 billion years ago, roughly 8 billion years after the galaxy began. There are stars in the Milky Way that formed billions of years before ours. If life developed around one of those early stars on a timescale similar to how it developed on Earth, that civilization would be billions of years ahead of us. Not thousands, not millions, billions. And a civilization with billions of years of technological development is something we can't easily imagine. But we can ask what we'd expect to see from it, and the answer, as the physicist Enrico Fermi noted at lunch one day in 1950, is probably more than nothing. That observation, the gap between the enormous probability of life existing somewhere and the complete absence of any evidence for it, is called the Fermi Paradox. And it's not really a paradox, it's a question. Where is everybody? In 1961, an astronomer named Frank Drake organized the first scientific conference on the search for extraterrestrial intelligence. To structure the discussion, he wrote an equation on a chalkboard. It's now called the Drake equation, and it's worth understanding what it says and what it doesn't say. The equation estimates the number of civilizations in the Milky Way that might be sending detectable signals right now. It does this by chaining together several factors: the rate at which new stars form in the galaxy, the fraction of stars that have planets, the fraction of those planets that could support life, the fraction of habitable planets where life actually develops, the fraction of life-bearing planets where intelligent life develops, the fraction of civilizations that develop technology capable of producing detectable signals, and finally, the average length of time such a civilization sends detectable signals. Most of these numbers we now know reasonably well. Stars form in the Milky Way at a rate of about 1 to 3 new stars per year. Most stars have planets. A significant fraction of planets are in habitable zones. Those numbers have been pinned down by observation. But the last several factors in the equation are almost completely unknown. The fraction of habitable planets where life develops, the fraction where intelligence develops, the fraction where technology develops, the length of time a civilization remains detectable. For these, we have essentially one data point, Earth. And one data point is no basis for statistical generalization. This is the honest state of the Drake equation. It's not a calculation, it's a framework for organizing our ignorance. When Drake first estimated the result with his best guesses, he got a number around 10 civilizations currently detectable in the Milky Way. Other scientists, using different assumptions, have gotten numbers ranging from 1 civilization, meaning us, to millions. The equation doesn't tell us the answer, it tells us which questions we'd need to answer to get the answer. But here's what's important. Even with conservative assumptions about how life and intelligence develop, the numbers in the Drake equation suggest that if civilizations routinely develop technology and persist for a reasonable time, the galaxy should be full of them. The silence therefore requires that one of those factors in the equation is much smaller than we'd naively expect. Either life rarely develops on habitable worlds, or intelligence rarely develops where life exists, or civilizations rarely develop technology, or they don't last long, or they develop technology but it doesn't produce anything we can detect. Something in the chain is broken. Something rare happened. The question is what? That question has generated what's now called the zoo of Fermi Paradox solutions, dozens of proposed explanations for the silence, and going through the serious ones tells us something important about both the universe and about ourselves. The most straightforwardly reassuring solution to the Fermi Paradox is this: we're simply the first. The galaxy is not, on cosmic timescales, very old. Life needed to wait for the universe to produce enough heavy elements, the carbon, oxygen, nitrogen, iron, and phosphorus that biological chemistry requires, and those elements come from exploding stars. You need at least 1 generation of stars to live and die before you have enough of the right ingredients for complex chemistry. That process took billions of years. Earth formed about 4.6 billion years ago, roughly 9 billion years into the universe's history. Life appeared on Earth remarkably quickly, within a few 100 million years of the planet forming and cooling, but intelligence, in the form of complex multicellular life took about 3.5 billion more years, and technological civilization took essentially all of recorded human history up to the Industrial Revolution, which is the last 200 years or so. 200 years is, relative to the age of the Earth, about the same as the last 4 seconds of a full day. The timing might not be a coincidence. Some researchers have argued that the universe itself has a kind of habitability history, a window in cosmic time that's hospitable for technological life. Too early and the heavy elements aren't available. Too late and stellar activity might be declining in ways that affect planetary stability. We might be close to the beginning of the habitable window, in which case most civilizations that will ever exist haven't arisen yet. This idea that we're early rather than alone has gained some traction in recent years. A 2016 analysis by astronomers at the Space Telescope's Science Institute found that 92% of Earth-like planets that will ever form in the universe haven't formed yet. If intelligence-bearing worlds are among the ones still to come, we might simply be at the leading edge of a galaxy that will eventually be populated with minds, but isn't yet. There's something strange about this possibility. If it's true, then we're not living in a universe that has developed and largely ignored us. We're living in a universe where life has just barely begun to appear. The long arc of cosmic time stretches out ahead of us, full of civilizations that don't exist yet, and we're the first light in an enormous room that's just starting to turn on. This is genuinely possible, but it requires that intelligence is rare enough that we happen to be first in a galaxy with hundreds of billions of stars. And that kind of luck is worth examining carefully. Here's where the explanation for the Fermi Paradox stops being reassuring and starts asking something more uncomfortable. It comes from an economist named Robin Hanson, who in 1998 wrote an essay that still gets cited constantly in serious discussions of this topic. Hanson introduced the concept of the Great Filter. The Great Filter is this: somewhere on the path from simple chemistry to a galaxy-spanning civilization, there's a step that almost nothing gets through. A filter, a barrier so difficult to cross that out of all the potential worlds that could produce technological civilizations, essentially none actually do. Or if they do, essentially none survive long enough to be detectable. That filter is why the galaxy is quiet. Now here's the thing: either the Great Filter is behind us, or it's ahead of us. If the Great Filter is behind us, we've already crossed it. We're the rare exception that made it through. The universe is full of dead worlds that never produced life, or worlds with primitive life that never developed complexity, or worlds with complex life that never developed intelligence, or intelligent species that never developed technology. And we somehow stumbled through all of those filters. This is actually a hopeful interpretation. If the hard part is already done, we might have a relatively clear path ahead. If the Great Filter is ahead of us, that's a different story. It means civilizations like ours typically reach this point, our point, and then don't get much further. Something destroys them, or stops them, or changes them. And whatever that something is, we haven't encountered it yet. The question of where the Great Filter sits is one of the most important questions we could possibly ask. And there are things we can observe that tell us something about the answer. Here's the uncomfortable logic. We know with reasonable confidence that life exists. It exists here. We know it took about 3.8 billion years from simple life to technology. That's a long time, which suggests some of the steps in the chain are genuinely hard. The more of those hard steps we've already crossed, the more the Great Filter is behind us, and the better our prospects look. But what would tell us that the Great Filter is ahead of us rather than behind? Finding life elsewhere. Here's why. If we found life on Mars, even simple microbial life, we'd know that life arises easily wherever conditions permit. That would push the Great Filter further along the chain. It would mean simple life isn't the hard step. And if simple life isn't the hard step is somewhere else, somewhere we haven't crossed yet. If we found intelligent life or technological civilization elsewhere, that would be worse news still. It would mean intelligence and technology aren't rare either, which means the great filter, the thing that makes civilizations vanish from the record, is something that hits after the development of technology. Something we've built, or are building, or are about to build. Something that waits for technological civilizations and takes them apart before they can spread across the stars. This is what makes the search for life such a complicated thing to hope for. If we find nothing anywhere, that's actually somewhat reassuring. It suggests the filter is behind us. We're rare. We made it through something hard. If we find life, especially complex life, the filter becomes more likely to be ahead. And the silence of the galaxy shifts from being a sign of our luck to being a warning. Hanson's essay is worth sitting with. It's not alarmist, it's just following the logic where it leads. Let's explore the candidates for a great filter that's already behind us, because if we've crossed it, we should be able to identify what it was. And some of these candidates are genuinely striking. The first candidate is the origin of life itself. Life on Earth appeared relatively quickly after the planet cooled, which might suggest it's easy, or might suggest we got lucky. We don't know. The chemistry that produced the first self-replicating molecules is still poorly understood. We've made significant progress on understanding prebiotic chemistry, the chemistry that could have preceded life, but we haven't reproduced the origin of life in a laboratory. We know it happened here. We don't know how easy it is. Some origin of life researchers think it's almost inevitable, wherever the right conditions exist. Others think it requires a series of highly improbable chemical coincidences, events so unlikely that even in a galaxy with tens of billions of habitable planets, only a handful of worlds produce life. If the origin of life is the filter, the galaxy is full of sterile, habitable worlds, forever waiting for chemistry that almost never quite works. The second candidate is the development of the eukaryotic cell. Most life on Earth, for the first 2 billion years, was prokaryotic, single-celled organisms without a nucleus, without mitochondria, without the complex internal architecture that makes complex multicellular life possible. Then, roughly 1.5 to 2 billion years ago, one of the most important events in the history of life occurred. A prokaryotic cell engulfed another prokaryotic cell, and instead of digesting it, kept it alive inside itself. The inner cell eventually became the mitochondrion, the organelle that powers virtually all complex life on Earth. This event, called endosymbiosis, happened essentially once in the history of life on Earth, or at least only one lineage of cells that underwent it survived and gave rise to all complex life we know. The biologist Nick Lane has argued that this event was so improbable, so contingent on a specific set of circumstances, that it might be the rarest step in the development of complex life. Prokaryotic life might be common throughout the universe. Eukaryotic life, and everything that comes from it, might be vanishingly rare. The third candidate is multicellularity. Complex multicellular organisms evolved from single-celled ancestors multiple times in the history of life on Earth. Animals, plants, fungi, and various algae all independently developed multicellularity. But the really complex multicellularity, the kind that produces differentiated tissues and organ systems, and the elaborate body plans that we associate with animals, evolved from a single common ancestor. That ancestor lived about 600 million years ago, and from it came every animal that has ever lived. The fourth candidate is intelligence itself. The brain of a human being is, in terms of the density and complexity of its neural connections, genuinely unusual. We have about 86 billion neurons, each one connected to an average of about 7,000 others. If every neural connection were a step on a staircase, with each step an inch high, the staircase would be long enough to reach the moon and back more than twice. And the way those neurons are organized, particularly the prefrontal cortex and its connections to the rest of the brain, seems to underlie the kind of recursive, abstract, future-oriented thinking that produces technology. Whether that level of neural organization is a common evolutionary outcome or a rare accident is genuinely unknown. Any of these could be the Great Filter, or the filter could be some combination of them, a series of small filters, each of which most worlds don't pass. The fact that we can't identify a single obvious answer is part of why the question is hard. Now here's the part that's harder to sit with. What if the Great Filter isn't behind us? What could it be if it lies ahead? The most immediate candidate is self-destruction through technology. Nuclear weapons have existed for less than 80 years. In that time, we've built enough of them to kill every person on Earth several times over. The current global nuclear arsenal contains about 12,500 warheads. Each of the largest warheads in use has a destructive yield of about 800 kilotons. To give that number some weight, the bomb dropped on Hiroshima had a yield of about 15 kilotons, and it killed between 90,000 and 166,000 people in a single moment. An 800 kiloton warhead is about 53 times more powerful, and there are thousands of them. That's just one category of existential technology. Engineered pandemics represent another. Advances in biotechnology, specifically in the ability to modify and design biological organisms, are occurring at a rate that would have seemed impossible 30 years ago. The same technology that allows researchers to develop vaccines and treatments also, in principle, allows the creation of pathogens designed for specific properties. As the knowledge and tools required to work with these technologies become more widely distributed, the risk that they'll be used destructively increases. Climate change is a longer timeline risk, but a real one. The chemical composition of Earth's atmosphere is changing as a result of fossil fuel combustion, and the consequences for global temperature, sea level, weather patterns, and agricultural systems are serious. Climate change is unlikely to cause human extinction on its own, but it could destabilize the complex systems, food, water, political stability that allow large technological civilizations to function. But here's the one that some researchers think is the most likely ahead of us filter. Advanced AI, a sufficiently capable artificial intelligence system, misaligned with human values or deployed in a context of severe geopolitical competition, could produce outcomes that no existing institution is designed to prevent. The philosopher Nick Bostrom and others have argued that the development of superintelligent AI, if not managed extremely carefully, could be the thing that takes technological civilizations to the point of development we've reached and then stops them. This is not science fiction. It's the considered position of some of the most serious researchers in the world, and the fact that we're building these systems right now, faster than we're developing governance frameworks for them, is the specific feature of our moment that makes this concern acute rather than theoretical. There's something worth sitting with here. If the Great Filter is ahead of us, it's probably not some external force, some cosmic predator or natural catastrophe. It's almost certainly something we do to ourselves, because the most capable civilizations, the ones that get far enough to be observable, would also be the ones with the most powerful technologies, and powerful technologies cut in both directions. Not all explanations for the silence are about filters and destruction. Some are about the nature of communication, or the nature of intelligence itself, or the structure of the universe in ways we might not have fully reckoned with. Let's go through the serious ones. The first is the "they're too far away" solution. Space is genuinely enormous, and the speed of light is genuinely slow relative to that enormity. The nearest star to Earth, Proxima Centauri, is about 4.2 light-years away. If Proxima Centauri had a civilization that sent a radio message toward us today, we'd receive it about 4.2 years from now. If we sent a reply, they'd get it 4.2 years after that. A full conversation would take nearly 9 years per exchange. But the Milky Way is 100,000 light-years across. A message from a civilization on the far side of the galaxy would take 100,000 years to arrive, and we've been searching for radio signals seriously for only about 65 years. A radio signal sent our way 65 years ago from the far side of the galaxy is still 99,935 years from reaching us. This matters because it means our current searches have only sampled civilizations within a sphere about 65 light-years in radius around Earth. The Milky Way is 100,000 light-years across, so that sphere samples about a 10 trillionth of the galaxy by volume. If we stack the whole galaxy into a pile the size of a football field, we've examined a patch about the size of a single blade of grass. So the too far away explanation has some force, but it has limits. A civilization with even a modest fraction of the time advantage we're imagining, thousands or millions of years of technological development, could potentially spread physical structures, not just signals, across significant portions of the galaxy. The physicist Freeman Dyson pointed out that a sufficiently advanced civilization might construct a shell around its star to capture all of its energy. A Dyson sphere or Dyson swarm would be detectable as an anomalous infrared source, a star giving off too much heat for its size. We've looked for these. We haven't found convincing evidence of one. The second solution is that they're using communications we're not listening for. Our search for extraterrestrial intelligence has focused primarily on radio waves, specifically a frequency called the water hole between 1.4 and 1.7 gigahertz that researchers in the 1970s identified as a plausible channel for interstellar communication. The reasoning was that hydrogen, the most abundant element in the universe, emits naturally at 1.4 gigahertz, and hydroxyl ions emit at 1.7 gigahertz. These frequencies bracket a relatively quiet part of the radio spectrum. An advanced civilization trying to communicate would know about these frequencies and might use them. But we've only been doing this for 65 years, and we've only examined a small fraction of the sky with sufficient sensitivity. And we're specifically looking for narrowband radio signals, the kind that would be obviously artificial. A civilization using different communication technology entirely, lasers, gravitational waves, modulated neutrinos, quantum channels, or something we haven't invented yet, would be entirely invisible to our current searches. Here's an analogy. Imagine you're in a city trying to find out if anyone lives there. You're equipped with a device that detects smoke signals. You search all week and find no smoke signals. You conclude the city might be uninhabited. But most cities don't communicate via smoke signals. Your detector is just tuned to the wrong thing. Our radio searches might be the cosmic equivalent of looking for smoke signals. The third solution is that they're not sending signals because they have no reason to. This is the dark forest hypothesis, articulated by the Chinese science fiction author Liu Cixin, but with serious roots in game theory. The argument goes, space is competitive, resources are finite. Any civilization that announces its existence risks being detected by a civilization that views it as a threat or a resource. The rational strategy for any sufficiently advanced civilization is to stay quiet, to avoid broadcasting its presence, and to treat any detected civilization as a potential threat. If this is true, the galaxy might be full of civilizations all hiding from each other, all listening but none transmitting, all aware that being found first is dangerous. The silence isn't absence, it's precaution. This is not a frivolous idea. It's derived from real game theory and real reasoning about how competitive systems work. The question is whether it applies to civilizations advanced enough to cross interstellar distances. Such civilizations would presumably have solved most of the resource scarcity problems that drive competition. Whether the logic of hiding applies to a civilization that can access the resources of an entire solar system is uncertain. The fourth solution is that interstellar travel and communication are so difficult that civilizations simply don't attempt them at scale. Even at 10% the speed of light, which is far beyond any technology we currently have, a journey across the Milky Way would take 1 million years. That's about 50 times longer than Homo sapiens has existed as a species. For a biological civilization, even a long-lived one, that's a significant undertaking. Perhaps the galaxy is full of civilizations, each confined to their home systems, exploring their local neighborhoods, building rich cultures and complex technologies, but never attempting to bridge the vast distances between stars because the cost in time and resources makes it impractical. In this picture, we're not alone, we're just isolated. Each civilization is an island, aware perhaps of its own existence, but unable to make contact with any other island in the sea. The fifth solution is one that's worth spending more time on because it touches something genuinely strange about how we think about intelligence and its future. Here's a possibility that most people haven't heard of, proposed by futurist John Smart in 2011. The transcension hypothesis suggests that the reason we don't see advanced civilizations expanding outward across the galaxy is because the direction of development for advanced intelligence consistently goes inward, not outward. The logic runs like this. The history of technology, at least in our experience, shows a consistent trend toward miniaturization and increasing information density. Early computers filled entire rooms. Now the most powerful computers in the world run on chips smaller than your thumbnail, with billions of transistors etched at scales measured in nanometers. A nanometer is about 10 times the width of an atom. This trajectory towards smaller, denser, more efficient computation shows no sign of reversing. Smart argues that an advanced civilization would pursue this inward trajectory to its logical conclusion. Rather than colonizing physical space, which is vast, cold, and energetically expensive, they would build increasingly compact computational environments. Eventually, they might be operating at the scale of atoms and subatomic particles, packing enormous computational complexity into vanishingly small physical volumes. An ultra-advanced civilization at this stage of development wouldn't look like a Dyson sphere around a star. It wouldn't look like radio transmissions spreading outward through the galaxy. It would look like nothing at all from the outside. It would be a dense knot of computational complexity, undetectable by anything we know how to look for. If this is what happens to civilizations, the galaxy might be full of entities that have turned inward, building their inner worlds to a richness we can't imagine, completely undetectable from outside. The universe would look empty to anyone scanning for traditional signs of technological activity, even though it's actually populated with civilizations operating at scales we haven't learnt to look for. This is speculative, but it's motivated by a genuine observation about the trajectory of technology, and it connects to a broader point about our assumptions. When we search for extraterrestrial intelligence, we're looking for civilizations that look like us at roughly our level of development, doing things we recognize as technological, but the civilizations that might be out there could be so different from us that we wouldn't recognize them if we saw them. Here's a connection that doesn't always get made explicit: the simulation hypothesis. The idea that our reality is a computational simulation run by some external intelligence has an interesting relationship to the Fermi Paradox. The simulation hypothesis has been formalized most carefully by philosopher Nick Bostrom in a 2003 paper. The argument is a trilemma. One of the following three statements must be true. Either virtually all civilizations at our level of development go extinct before reaching the capability to run detailed simulations of their ancestral history, or virtually no technologically mature civilizations choose to run such simulations, or we're almost certainly living in a simulation. This is a serious logical argument with uncomfortable implications. If civilizations routinely survive and develop the capability to run historical simulations, and if they choose to, there would be vastly more simulated civilizations than real ones, probably by a factor of billions or more. By simple probability, you'd expect to be in a simulated civilization rather than a real one. The connection to the Fermi Paradox is this. If we're in a simulation, the operator of the simulation might simply not have populated it with other civilizations. Perhaps the simulation is specifically about us, running only enough background to make our experience coherent. The universe would be a backdrop, mostly empty, with us as the intended subjects of the simulation. This would explain the silence. There are no other civilizations because there's no need to simulate them. This might sound like unfalsifiable speculation, and in a direct sense it is. You can't distinguish from inside a simulation whether it's a simulation or not, but it has at least one implication that's testable in principle. If the simulation has finite computational resources, it might economize by not running fine-grained physics in regions nobody's looking at. Some physicists have speculated about what signatures of this economizing might look like, specific patterns in the cosmic microwave background, or discretizations in the fabric of space-time at very small scales. None of those signatures have been found, but we've barely started looking. And the deeper point stands: the simulation hypothesis is one of the few Fermi Paradox solutions that doesn't require the universe to be mostly sterile or civilizations to be mostly doomed. It just requires the universe to be artificial, which is either a comforting or deeply unsettling thought, depending on how you hold it. Let's be specific about what we've actually done in the search for extraterrestrial intelligence, because the gap between the scale of the search we've conducted and the scale of what we'd need to do to draw real conclusions is itself important. The first serious search for radio signals from space began in 1960. An astronomer named Frank Drake pointed a radio telescope in Green Bank, West Virginia, at two nearby stars, Tau Ceti and Epsilon Eridani, both roughly 12 light-years away, and listened for about 200 hours. He heard nothing artificial. The project was called Ozma, named after the ruler of the land of Oz, and it was the beginning of a search that's been ongoing in various forms ever since. The most famous moment in SETI, the search for extraterrestrial intelligence, came in August 1977. Jerry Amon, a volunteer researcher working at the Big Ear Radio Telescope at Ohio State University, was reviewing data printouts and found a signal that stood out so dramatically from the background noise that he circled it and wrote "Wow" in the margin. The signal, now called the WOW signal, lasted 72 seconds, which was the limit of how long the telescope could observe a fixed point in the sky. It appeared to come from the direction of the constellation Sagittarius and matched several of the expected characteristics of an extraterrestrial signal. The WOW signal has never been observed again. Researchers have pointed the most sensitive radio telescopes at that region of sky dozens of times, using equipment far more capable than what Big Ear had in 1977, and found nothing. Whether it was a genuine signal from an extraterrestrial source, a natural astronomical phenomenon, or interference from some undiscovered source here on Earth, remains unknown. It's one of the most frustrating open questions in the entire field. Since then, the scale and sensitivity of SETI searches has grown substantially. The Breakthrough Listen initiative, funded by investor Yuri Milner with a pledge of $100 million over 10 years, began in 2015. That $100 million represents roughly the cost of a mid-size office building in a major city. For context, NASA's budget for Mars exploration in 2023 was about $2.5 billion. The SETI field has always been underfunded relative to its importance. Breakthrough Listen uses some of the largest radio telescopes in the world, including the Parkes Observatory in Australia and the Green Bank Telescope in West Virginia, which has a dish 100 meters across, roughly the length of a soccer field. It surveys the nearest million stars, the galactic center, and dozens of nearby galaxies. It generates more data in a single day than previous SETI projects generated in a year. And it has found no confirmed artificial signals. Here's an important caveat about what this means. Breakthrough Listen, as of 2024, has surveyed roughly 1 million stars with high sensitivity. The Milky Way has between 200 and 400 billion stars. 1 million stars is about 1 in every 200,000 to 400,000 stars in the galaxy. That's a sample fraction of about 0.0005%. If you applied that same sampling fraction to the population of Earth, you'd be trying to understand global human civilization by talking to about 40,000 people, all of whom happen to be your nearest neighbours. You'd get a very limited picture. This doesn't mean the search is worthless. It means we should be honest about what conclusions we can draw from it. The absence of a detected signal tells us that no civilization within roughly 1,000 light-years of Earth is broadcasting a powerful, narrow-band radio signal at the specific frequencies we've been monitoring. That's a meaningful constraint, but it doesn't tell us much about the rest of the galaxy or about civilizations using different communication methods. The honest state of the search is this: we've done a genuine amount of work with the resources we've had, and we've established that certain specific kinds of signals don't seem to be coming from nearby stars, but we haven't remotely scratched the surface of the search that would be needed to conclude the galaxy is quiet. Radio signals are just one type of thing we might look for. Researchers have increasingly broadened the search concept to what they call techno-signatures, any observable sign that technology exists somewhere. This widens the search space considerably. One category is atmospheric signatures. If a planet has life, its atmosphere should be chemically different from a planet without life. Oxygen, for example, is highly reactive. It bonds to rock and metals and other molecules. On a planet without life, constantly replenishing it through photosynthesis, atmospheric oxygen would disappear in a geologically short time. Earth's high oxygen content is itself a biosignature, a sign that something biological is going on. When the James Webb Space Telescope, which launched in December 2021 and has a mirror 6.5 meters across, about the height of a two-story building, began observing distant exoplanets, one of its primary goals was to detect atmospheric signatures. Industrial signatures are a more specific techno-signature. Our own industrial activity has altered Earth's atmosphere in detectable ways, specifically through the accumulation of certain molecules that don't occur naturally in large quantities. Chlorofluorocarbons, the compounds that damaged the ozone layer before they were banned, are one example. They're entirely synthetic. If a telescope detected CFCs in the atmosphere of a distant planet, that would be strong evidence of industrial activity, because there's no natural process that produces them in significant quantities. Another type of techno-signature is waste heat. Any civilization using significant energy would generate heat as a byproduct because the laws of thermodynamics require it. A civilization using the energy of an entire star would radiate that energy primarily as heat at a temperature characteristic of its technology, significantly different from the star's natural emission. Astronomer Jason Wright and colleagues have searched existing astronomical databases for stars with anomalous infrared signatures, potential signs of megastructures capturing and re-radiating energy. They found candidates, unusual stars with excess infrared emission, but nothing with a convincing case for artificial origin. The star KIC 8462852, nicknamed Tabby's star after astronomer Tabetha Bayagian, who first studied it carefully, became briefly famous in 2015 when researchers found it dimmed in ways unlike any known natural phenomenon. It didn't dim regularly like a planet transit. It dimmed sporadically, by amounts ranging from 1 to 22%, in patterns that didn't fit models for any known astronomical object. For a time, some researchers considered the possibility that the dimmings were caused by artificial megastructures in orbit. That earned it the nickname the alien megastructure star in popular press coverage. Subsequent observations and analysis led most researchers to conclude that the dimmings are more likely caused by dust, possibly from disintegrating comets or asteroids. But the process of elimination that led to that conclusion was itself valuable. Tabby's star showed that even an unusual, hard-to-explain signal can have natural explanations, and that we need to be much more careful than initial excitement might suggest about what we're actually seeing. Here's what the search for techno-signatures tells us in its current state. we've found nothing artificial. We've found many genuinely unusual and interesting natural phenomena, and we've learned that the universe is full of processes that produce signals we don't immediately understand, which means distinguishing the artificial from the natural is harder than it might seem. But the search is getting better. James Webb is detecting the molecular composition of exoplanet atmospheres in ways that were impossible before it launched. New radio telescope arrays are increasing our sensitivity by orders of magnitude, and machine learning is being applied to astronomical datasets to search for patterns that human eyes might miss. The next decade of searching will be qualitatively different from anything that's come before. Here's something that gets underappreciated in discussions of the Fermi Paradox. When we search for extraterrestrial intelligence, we're projecting our own definition of intelligence onto the universe. But intelligence might take forms that we'd have difficulty recognizing, even if we encountered them. Consider what we might have looked like to an alien observer visiting Earth 300 million years ago. Forests covered much of the land. Complex ecosystems thrived in the oceans. There were hundreds of thousands of species with brains, engaged in hunting, fleeing, reproducing, and navigating complex social environments. A visiting intelligence might well have detected life, might have detected biological complexity, but they'd have found no signs of technology, no radio emissions, no alterations of the planet's chemistry beyond what biology produces, no structures visible from space. Now visit again 3 million years ago. Early hominids are walking upright, using simple stone tools, nothing detectable from orbit. Visit again 10,000 years ago. Agriculture has begun, forests are being cleared, small settlements are forming, still nothing detectable from space except perhaps some minor alteration in land cover. Visit 200 years ago, right at the dawn of industrialization. Now you can detect things. Atmospheric chemistry is beginning to change. Structures are appearing at scales visible from low orbit. In the long arc of a civilization's development, the window during which it's detectable by our current methods might be narrow. Before radio, we were quiet. During the radio era, we broadcast unconsciously into space. After radio, we might go mostly quiet again, as we shift to tightly focused laser communication and encryption that resembles random noise. The detectable window might be measured in centuries rather than millennia. Apply that to the galaxy. If detectable civilizations exist for only a few centuries before transitioning to forms of communication we can't detect, then at any given moment only a tiny fraction of all the civilizations that have ever existed would be detectable. The galaxy might have hosted millions of technological civilizations over its 13 billion year history, each one burning brightly in the radio spectrum for a few hundred years and then going quiet. We'd be searching a vast ocean for a candle that's already been extinguished. This doesn't mean the civilizations are gone. It means they might simply no longer be in the habit of broadcasting loudly in every direction. Think about how our own broadcasting has changed. In the 1950s, powerful television and radio signals were broadcasting outward into space. We weren't trying to send messages to aliens, we were just using radio, and the signals escaped into space. The edge of that bubble of radio noise, travelling at light speed, is currently about 75 light-years from Earth. A sphere 150 light-years across, centred on Earth, contains a bubble of television signals going out in all directions. I Love Lucy is currently about 70 light-years from Earth. But since the 1980s and 1990s, broadcast television has been declining in favour of cable and satellite delivery, which uses much tighter beams pointed at specific receivers. Streaming is more efficient still. The total power of our accidental broadcasts into space has been declining. We're becoming harder to detect, not through any intention to hide, but simply because our technology is becoming more efficient. This might be a universal feature of technological development. Early technology is loud and inefficient. Mature technology is quiet and precise. If that's right, the brief window during which a civilization is easily detectable might be early in its technological development, before it has learned to be precise, and after that it becomes essentially invisible to anyone not knowing exactly where to look. Here's one of the more quietly troubling framings of the Fermi Paradox. We've talked about the possibility that we're the first, that we're early in cosmic history and most civilizations haven't arisen yet, but there's an equally coherent possibility that we're the last, or nearly the last. Not the last to arise, but the last to survive. The cosmologist Lee Smolin proposed an idea called cosmological natural selection, where universes that produce black holes are more likely to produce other universes. In his picture, universes that are good for producing stars and black holes are also good for producing life. This is speculative physics, but it suggests a universe tuned toward life in general. If the universe is tuned toward life, and life has been arising for billions of years, then where is it all? One answer is that it arises, it develops technology, and it collapses. Not necessarily through war or disease, perhaps through the fundamental dynamics of what happens when any civilization reaches a certain level of capability. Perhaps technological civilizations have a characteristic lifespan, and ours is approaching its end. Perhaps every advanced civilization reaches the moment where its capabilities exceed its wisdom and it enters a final chapter. This is the late filter hypothesis in its most direct form, and the evidence for it is, honestly, troubling. We've had nuclear weapons for less than 80 years. Climate change is accelerating in ways that are difficult to manage politically. Advanced biotechnology is spreading faster than biosecurity can adapt. AI development is proceeding faster than governance. These aren't hypothetical future risks, they're real, present dynamics that serious people take seriously. If we looked at our civilization from the outside, from the perspective of a long-lived galactic observer who had watched thousands of civilizations rise and fall, what would they say about our current moment? They might say, this is the phase. This is the transition where capabilities outrun wisdom. This is where they either figure out coordination and survival, or they don't. Most don't. That's a sobering thought. It's also the thought most worth acting on. In 2000, paleontologist Peter Ward and astronomer Donald Brownlee published a book called Rare Earth: Why Complex Life is Uncommon in the Universe. Their argument was that the conditions that produced complex life on Earth are not just uncommon, they're extraordinarily specific, and the implication is that complex life, especially intelligent life, might be so rare that Earth could be unique or nearly unique in the observable universe. The rare Earth argument has several components. Let's go through them. The first is the location of Earth within the Milky Way. We're in the galactic habitable zone, roughly 2/3 of the way from the center of the galaxy to the outer edge. The galactic center is denser, with more stars and more supernovae, which are stellar explosions that can sterilize nearby planets. The very outer edge has fewer heavy elements because it's been enriched by fewer stellar generations. The middle regions have both the stability and the enrichment necessary for complex chemistry. About 20% of stars in the Milky Way are in this habitable zone, so it's not rare in an absolute sense, but it matters. The second is the nature of our star. The Sun is a G-type star, relatively stable, with an output that's varied by only about 0.1% over the last 400 million years or so. Many stars are more variable. Red dwarf stars, which are the most common type in the galaxy, making up about 70% of all stars, are prone to powerful flares that can strip planetary atmospheres, especially for planets in the habitable zone, which for a dim red dwarf star is very close in. Orbiting too close to a flaring star might be problematic for complex surface life. The Sun is calmer than most stars. The third is the existence of Jupiter. Our solar system's largest planet, Jupiter, has a mass 318 times that of Earth. If you gathered all the material of every planet in the solar system except the Sun, more than half of it would be Jupiter. At that size, Jupiter has significant gravitational influence on the inner solar system. Some researchers believe that Jupiter's gravity has deflected many comets and asteroids that would otherwise have struck Earth, reducing the frequency of mass extinction events. Others argue Jupiter also sends objects inward. The net effect is debated, but Jupiter's influence on the inner solar system is real. The fourth is the Moon. Our Moon is large for a planetary moon, about 1/4 of Earth's diameter. That's unusually large relative to the planet it orbits. The Moon stabilizes Earth's axial tilt, which is currently about 23.5 degrees. Without the Moon's stabilizing influence, Earth's axial tilt might vary wildly over time, ranging from near zero to over 85 degrees, dramatically changing seasonal patterns and climate stability. Life might have found much more difficult conditions to adapt to without a stable axial tilt. The fifth is plate tectonics. Earth is one of the few rocky planets we know of that has active plate tectonics, the ongoing movement of continent-sized plates of crust. Plate tectonics drive the carbon cycle, the process by which carbon dioxide is absorbed from the atmosphere into rocks and then released again through volcanism. This cycle acts as a thermostat for the planet over long timescales, helping to keep temperatures within a range that allows liquid water. Without plate tectonics, Earth might have experienced runaway greenhouse warming or permanent glaciation long ago. Taken together, the rare Earth hypothesis suggests that the specific combination of factors that produced complex life on Earth is genuinely uncommon. Not impossible elsewhere, but rare enough that the expected number of complex life-bearing worlds in the observable universe might be small, possibly much smaller than one. If this is right, we really are alone or nearly alone, and the Fermi Paradox dissolves because there's nothing to hear. The silence is just reality. Critics of the rare Earth hypothesis argue that it commits the error of assuming that life needs conditions like Earth's. If life can exist in different chemical forms, at different temperatures, around different types of stars, then the specific conditions of Earth might be one of many viable configurations rather than the only one. Life under ice on ocean worlds, life in dense atmospheres, life at temperatures we'd consider extreme. The universe has many unusual environments, and dismissing all of them as uninhabitable might say more about our imagination than about life's requirements. There's a possibility that doesn't get enough attention in discussions of the Fermi Paradox. It's called Panspermia, and it's the idea that life doesn't have to originate independently on each world where it exists. Life might spread. We know that rocks have been exchanged between planets in our solar system. Mars meteorites have been found on Earth. Earth meteorites presumably exist on Mars. When a large asteroid or comet impacts a planet with enough force, it ejects material at escape velocity, and some of that material can travel to other planets. The journey between Mars and Earth takes between months and years depending on orbital geometry. Some microorganisms can survive in the extreme conditions of space, vacuum, radiation, temperature extremes, for timescales relevant to those journeys. In 1996, NASA announced that a meteorite from Mars, known as ALH 84001, appeared to contain microfossils of ancient Martian bacteria. The rock was about 4 billion years old, formed when Mars was warmer and wetter. The announcement was a major news event. Subsequent analysis has been less conclusive, and most scientists today are skeptical that the features in ALH 84001 are biological. But the question of whether the meteorite contains biological traces has never been definitively closed. If life can spread between planets in our own solar system, it might be able to spread between star systems. The timescales are much longer. Rocks ejected from one stellar system in a supernova or large impact might travel between star systems over millions of years. Some fraction of the material ejected from one solar system might eventually be captured by another. If hardy microorganisms can survive millions of years in space, trapped inside rocks that protect them from radiation, the galaxy might have been seeding itself with life throughout its history. This idea is called Panspermia, meaning the spreading of life via rocks, and while it's speculative, it's not ruled out by any known physics or biology. The implications for the Fermi Paradox are mixed. If Panspermia is real, life might be more common than independent origin calculations suggest, because you need only one origin event rather than one per world. But Panspermia spreads simple life, not intelligence. The filters that matter might still apply to the development of complexity and technology from whatever simple life arrives. There's a more radical version of Panspermia called directed Panspermia, the intentional seeding of life across the galaxy by a technological civilization. The co-discoverer of DNA, Francis Crick, proposed this seriously in a 1973 paper. The idea is that an advanced civilization, perhaps knowing its world was doomed, might have deliberately seeded other worlds with the building blocks of life or with simple organisms. If our own life traces to such a deliberate seeding, we'd be the descendants of a civilization that lived and died billions of years ago with no way to know it. This is untestable in any obvious way, but it's not incoherent, and it means the origin of life on Earth might tell us something about an entirely different world and civilization, rather than just about Earth's natural chemistry. We've spent a lot of time on what we've listened for. Let's talk about what we've said. In 1974, the Arecibo radio telescope in Puerto Rico, with a dish 305 meters wide, roughly the size of a small airport runway, broadcast a message toward a globular cluster called M13. M13 is a tight ball of about 300,000 stars, about 25,000 light-years from Earth. The Arecibo message was a 679-character binary transmission that encoded a graphic representation of information about humans and Earth, our number system, the elements of DNA, a figure of a human being, our solar system, and the Arecibo telescope itself. The message will take 25,000 years to reach M13. If anyone there receives it and replies immediately, we'd get their reply about 50,000 years from now. In 50,000 years, modern humans might not exist. Human civilization might not exist in any recognizable form. The Arecibo message was more a statement about our existence and our capabilities than a practical attempt to establish communication. The Pioneer plaques are another example. In 1972 and 1973, NASA attached gold anodized aluminium plaques to the Pioneer 10 and Pioneer 11 spacecraft. The plaques show a man and a woman, a diagram of hydrogen's hyperfine transition that provides a universal unit of measurement, a graphic representation of our location in the galaxy using 14 pulsars as landmarks, and a diagram of our solar system showing the spacecraft's trajectory. Pioneer 10 has now traveled about 130 astronomical units from the Sun. 1 astronomical unit is the distance from Earth to the Sun, about 93 million miles. So Pioneer 10 is about 12 billion miles from home, or about 17 times farther from the Sun than Neptune. At its current speed of about 27,000 miles per hour, it would take roughly 80,000 years to reach the nearest star if it were pointed at it. It isn't. The Voyager golden records are more elaborate. Both Voyager 1 and Voyager 2, launched in 1977, carry gold-plated copper phonograph records containing sounds and images from Earth. The record includes sounds of nature, music from around the world, spoken greetings in 55 languages, and a printed message from President Carter. Voyager 1 is now roughly 23 billion miles from the Sun, traveling at about 38,000 miles per hour, fast enough to get from Los Angeles to New York in under 5 minutes. Even at that speed, it won't pass close to another star for about 40,000 years. These messages are artifacts rather than communication. They're more like messages in a bottle thrown into an ocean the size of the galaxy than practical attempts at conversation. But they say something interesting about what we've chosen to say about ourselves when given the chance. We sent our science, our music, our sounds, our bodies. we sent what we thought was most essential about us. Whether anyone will ever find them and be able to interpret them is essentially unknowable. There's a live debate in the SETI community about whether we should be actively transmitting, whether we should be trying harder to announce our existence. One side argues that if all civilizations are reluctant to transmit, the galaxy stays quiet even if it's full of life, and someone has to go first. The other side argues that announcing our existence to an unknown universe before we've established that the universe is safe is a profound risk to take on behalf of all of humanity without any meaningful democratic deliberation. The debate has no clear resolution. We've never voted on it. We've never had a global conversation about it. A handful of researchers and radio telescope operators make decisions about what we broadcast into space without any formal accountability to the rest of the species. Let's talk about what's happening right now in the search for life beyond Earth, because the pace of discovery has accelerated dramatically in the last few years. The James Webb Space Telescope represents the sharpest eyes humanity has ever pointed at the stars. Its primary mirror is 6.5 meters across and composed of 18 hexagonal segments coated in gold. Because gold reflects infrared light with nearly perfect efficiency, the telescope is currently positioned at a point called L2, which is about 1 million miles from Earth in the direction away from the Sun. At that distance, if you held a pencil at arm's length, the pencil would appear roughly twice as large as the telescope. James Webb's primary scientific focus is on the early universe and on exoplanet atmospheres. For our purposes, the exoplanet work is what matters. Webb can detect the atmospheric composition of planets orbiting other stars by observing how starlight filters through a planet's atmosphere as the planet passes in front of its star. Different molecules absorb different wavelengths of infrared light, leaving specific fingerprints that Webb can read. In 2023, Webb detected the molecular signature of dimethyl sulfide in the atmosphere of a planet called K218b, about 120 light-years from Earth. Dimethyl sulfide on Earth is produced almost exclusively by marine phytoplankton. It's a potential biosignature. The detection was preliminary, and the researchers were careful to note that it requires confirmation and that non-biological processes might also produce the molecule. K218b is a sub-Neptune planet, larger than Earth, with a deep atmosphere that doesn't look like anything in our solar system. Whether its conditions are compatible with life is genuinely uncertain. But the fact that we can now detect potential biosignatures in the atmosphere of a planet 120 light-years away, where 120 light-years is the distance that light, moving at 186,000 miles per second, covers in 120 years, represents a genuine turning point in the search. We're not just hypothesizing about whether we could detect life on other worlds. We're actually doing it, imperfectly, with our current best technology. The next generation of telescopes being planned will push this further. The Habitable Worlds Observatory, currently in conceptual development at NASA, is designed specifically to search for biosignatures on nearby Earth-like planets. The European Extremely Large Telescope in Chile, when it completes construction, will have a primary mirror nearly 40 meters across, roughly the height of a 13-story building, and will be capable of directly imaging nearby Earth-like planets and analyzing their atmospheres. We're at the beginning of an era in which the question of whether life exists elsewhere is moving from philosophical speculation to empirical investigation. We might have the answer, or at least a much better constrained probability, within a generation. One of the most significant shifts in astrobiology over the last 30 years is the expanding definition of what counts as a habitable environment. For most of human history, we thought life required sunlight. Photosynthesis was assumed to be the foundation of essentially all life. Then in 1977, researchers exploring the deep ocean floor using a submersible found something that changed that assumption. At a depth of 2.5 kilometers below the ocean's surface, in complete darkness, Under pressure, about 250 times greater than at the surface, they found hydrothermal vents, cracks in the ocean floor where superheated, mineral-rich water bubbles up from the Earth's interior. And around those vents, they found thriving ecosystems, tube worms meters long, clams, crabs, shrimp, bacteria, all of them living in total darkness, powered not by sunlight but by chemosynthesis, energy from chemical reactions between the vent fluids and the cold seawater. This discovery was genuinely paradigm-shifting. It meant that sunlight wasn't a requirement for life. Wherever there was liquid water and a chemical energy source, life could potentially exist. And that opened up an enormous range of environments that had previously been assumed to be lifeless. In our own solar system, several worlds now appear to have subsurface liquid water. Europa, a moon of Jupiter, is covered by a shell of ice that may be 10 to 30 kilometers thick. Beneath that ice, there's evidence for a global ocean of liquid salt water, possibly 100 kilometers deep. That ocean contains roughly twice as much water as all of Earth's oceans combined. And Europa also has a rocky seafloor. If hydrothermal vents exist on that seafloor, the conditions for chemosynthetic life would be present. Enceladus, a moon of Saturn, has been even more revealing. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, flew directly through a plume of material venting from cracks in Enceladus's south pole. The plume contained water vapor, ice particles, molecular hydrogen, silica nanoparticles, and complex organic molecules. Molecular hydrogen in that context is particularly interesting because on Earth, the reaction between water and hot rock that produces hydrogen, called serpentinization, is one of the energy sources that powers deep-sea hydrothermal vent ecosystems. Finding molecular hydrogen in the Enceladus plume suggests that similar chemistry is happening on its seafloor. Titan, another moon of Saturn, has lakes and rivers of liquid methane and ethane on its surface. It's so cold that water ice is as hard as rock there, and methane behaves like water. Some researchers have proposed that life based on methane chemistry rather than water chemistry might exist on Titan. It would be life as we don't know it, with a completely different biochemistry, but the possibility exists. The implication for the Fermi Paradox is that the number of habitable environments in the universe might be vastly larger than the number implied by counting rocky planets in the liquid water zone of their stars. Ocean worlds, subsurface liquid water environments, and exotic chemistry worlds might all harbour life. If that's right, the universe is probably full of simple life, and the great filter, if it exists, probably lies somewhere between simple life and the technological civilization that could make itself heard across interstellar distances. Beyond searching for signals, some researchers are exploring whether we could physically reach other star systems and search more directly. The distances involved are genuinely challenging, but there's one proposed approach that's worth understanding. Breakthrough Starshot, another initiative by Yuri Milner, is a proposal to send tiny robotic spacecraft to Alpha Centauri, the nearest star system to Earth, at about 4.2 light-years away. The spacecraft would be gram-scale chips with cameras, computers, and communication lasers attached to ultra-thin light sails, perhaps a few meters wide. A powerful laser array on Earth would push those sails to roughly 20% of the speed of light, fast enough to make the journey in about 20 years. At 20% of the speed of light, which is about 37,000 miles per second, the little spacecraft would pass through the Alpha Centauri system and take pictures and measurements before sailing onward into space. The images and data would then be transmitted back by laser, taking about 4.2 years to reach Earth. Total mission time from launch to data receipt, about 25 years. The technical challenges are immense. A laser array powerful enough to accelerate a sail to 20% of light speed would need to be gigawatts in power, roughly the output of a large nuclear power plant operating for a few minutes. The sail would need to survive the heating from that laser, The chip would need to survive 20 years in interstellar space with cosmic ray bombardment, and the communication laser on a gram-scale spacecraft needs to be precise enough to hit Earth from 4.2 light-years away. None of this exists yet, but none of it obviously violates physics. The initiative has attracted serious scientists and engineers to work on the component challenges. If it ever launches, it would be humanity's first direct investigation of another star system. And if it found something unexpected in the Alpha Centauri system, an atmosphere around its rocky planet Proxima Centauri b, anomalous infrared emissions, anything at all, it would fundamentally change the conversation. But even at 20% of the speed of light, a journey to the center of the Milky Way would take about 250,000 years, and a journey to the far side of the galaxy would take about 500,000 years. Physical exploration of the galaxy is not an option on any timescale we can currently conceive of for biological humans. Whatever we learn about the rest of the universe in the near future will come from looking and listening, not from going. Before we leave the solar system, it's worth spending time on Mars, because Mars is the most accessible place to look for evidence of past life, and what we find or don't find there will tell us something important about how common life is. Mars today is cold and dry, with an atmosphere about 1% as dense as Earth's, made mostly of carbon dioxide. The surface is bathed in ultraviolet radiation and bombarded by cosmic rays, making it inhospitable for most life as we know it. But Mars wasn't always like this. About 3.5 to 4 billion years ago, Mars had a thicker atmosphere, a warmer climate, and liquid water on its surface. We know this from the mineralogy of Martian rocks, which contain clays and sulfates that form in the presence of liquid water, and from the ancient riverbeds and lake floors that NASA's rovers have been exploring. The Perseverance rover, which landed on Mars in February 2021, is operating in a region called Jezero Crater, which scientists believe was once a lake. Perseverance is specifically designed to search for signs of ancient microbial life. It's been collecting rock cores from locations that would have been most promising for microbial habitation billions of years ago. Those cores are being cached on the Martian surface in titanium tubes, waiting for a future sample return mission to bring them to Earth. If life existed on early Mars, and if it was similar enough to Earth life to produce recognizable biosignatures, we might detect those biosignatures in the returned samples. The analysis would take years and would involve the most sensitive techniques in astrobiology, but we'd be looking at actual samples from a world with confirmed ancient habitability. If we find no biosignatures in those samples, that's informative. It suggests that life didn't develop on Mars even when conditions were favorable, which would support the idea that the origin of life is a rare event. If we find biosignatures, the implications are enormous. It would mean life arose independently at least twice in our solar system. And if it arose twice in our solar system, which is a very small neighborhood of the galaxy, it almost certainly arises frequently across the galaxy, which would push the Great Filter further along the chain toward intelligence or technology or lifespan, which would make the Fermi Paradox more acute, not less. The Mars sample return is one of the most scientifically important missions in the history of space exploration. It's also significantly over budget and delayed. The current timeline has the samples reaching Earth sometime in the 2030s. The result, whatever it is, will be one of the most consequential scientific findings in human history. Let's be concrete about something we rarely discuss. What would actually happen if we detected a signal from an extraterrestrial civilization? There are protocols. The International Academy of Astronautics has a declaration of principles for activities following the detection of extraterrestrial intelligence. The protocols call for verifying the signal, reporting to the scientific community, informing governments and international organizations, and eventually crafting a collective international response. In practice, whether these protocols would hold in the face of an actual detection is uncertain. A detected signal would be the biggest news event in the history of our species, and controlling the flow of information for any significant period would be extremely difficult. Social media and the speed of modern communication would make the protocol's measured pace essentially impossible to maintain. Within hours of a detection becoming known to anyone outside a small circle, it would be public. The geopolitical implications would be significant. Which country detected the signal? Does that country have some special claim? What is the content of the signal? Is it a simple beacon announcing existence, or something that conveys information? If it conveys information, how is the interpretation process organized, and who has authority over the response? These aren't hypothetical policy puzzles, they're real governance challenges that we haven't solved. There's no international treaty governing what happens after contact. There's no international body with the authority to speak for humanity if a response is warranted. The UN Committee on the Peaceful Uses of Outer Space deals with the practical governance of human activities in space. It doesn't have protocols for extraterrestrial contact. Nobody does. The content of a detected signal would matter enormously. A simple, regular pulse that announces existence but carries no information is one thing. A message that can be decoded and that contains information about another civilization's biology, physics, mathematics, or history is another thing entirely. The possibility that an alien signal might contain something we shouldn't receive, a computer virus for a technological civilization, dangerous physics, or psychologically harmful content, is taken seriously by some researchers. These are called information hazards, and they're worth thinking about before we're in a position of having to decide in real time. The honest answer about what would happen is, we don't know. We haven't prepared adequately. The protocols are better than nothing, but they're not sufficient, and the governance gap that exists for AI and for other transformative technologies exists for this scenario too. We're developing capabilities, in this case the capability to detect extraterrestrial signals, faster than we're developing the institutional frameworks for managing the consequences. Here's what I think is genuinely possible over the next half-century, based on the trajectory of the search and of our technology. Within the next 20 years, we will likely have the capability to definitively characterize the atmospheres of dozens of nearby Earth-like planets. If any of them show robust biosignatures, the strong presence of oxygen, methane, and other biologically produced gases in chemical disequilibrium, we'll know. Not with certainty. Science doesn't give certainty, but we'll have strong evidence for or against life on specific, named worlds within a few dozen light years of Earth. Within the same time frame, Mars sample return will give us direct evidence about whether life arose on Mars. That result will either confirm that life is common in our solar system, or tell us something important about the rarity of abiogenesis. Within 30 to 50 years, radio and optical SETI searches will have surveyed the entire Milky Way galaxy at sensitivities that significantly exceed anything possible today. If a civilization anywhere in the galaxy is broadcasting with the power that our own civilization broadcasts, we'll be able to detect it. If we find nothing, that constrains the number of broadcasting civilizations very tightly. Breakthrough Starshot-style missions, if they develop as planned, could give us direct observations of the nearest star systems within 30 to 40 years. We'd have images and atmospheric data for Proxima Centauri b, the rocky planet in the habitable zone of our nearest stellar neighbour. That data would be extraordinary. The combination of these capabilities means the Fermi Paradox will have a much better constrained answer within the lifetime of many people alive today. We won't necessarily know the complete answer, but we'll have moved from speculation to data in a way that's qualitatively different from where we are now. The most important thing to understand about the next 50 years of this search is that we're not just looking for company, we're looking for information about our own situation. If we find simple life, that tells us the great filter is ahead. If we find no life anywhere in a thorough search, that might tell us the filter is behind us. Whatever we find, it tells us something about what we are and what we might become. There's a dimension to the Fermi Paradox that rarely comes up in scientific discussions: the psychological dimension. The fact that the silence of the universe, when you sit with it properly, has a weight that's hard to describe. We're a species that evolved in a rich social environment, surrounded by other minds. Our brains are wired to find minds everywhere. We see faces in clouds and wood grain. We attribute intentions to animals and storms and the motion of shapes on a screen. We're deeply social, deeply oriented toward other minds. The idea that we might be alone, not just alone in terms of intelligent life on our planet, but alone in a meaningful sense in the entire observable universe, runs against something very deep in what we are. And yet the silence makes that possibility real. Not certain, but real. Carl Sagan, who spent his career at the intersection of science and the search for meaning, often wrote about the loneliness of the cosmos and the importance of doing this search. He believed that finding other life would transform humanity's self-understanding in ways that nothing else could. In his 1985 novel Contact, he tried to imagine what that transformation might look like. He also said something that's worth keeping in mind now: when the silence is still our only answer, the universe is a pretty big place. If it's just us, seems like an awful waste of space. The waste of space framing is interesting. It implies that a universe full of life is more purposeful, more worth having, than a universe with only one example. But the universe doesn't operate on human notions of waste and purpose. It does what physics says it does. And if physics produces intelligent life only rarely, or only once, that's what it does. The universe's vastness is not a moral argument for company. But here's what the vastness is. It's an opportunity. We're a species that has been curious about the sky since before we had words for our curiosity. We've mapped the stars, built instruments to see farther and farther, and now we're beginning to ask the question directly, with real tools, about whether anyone is out there. The fact that we're asking is itself worth something. The search is worth something, not just because of what we might find, but because of what the act of searching says about what kind of thing we are. We're the part of the universe that's become curious about itself. If we're alone, that curiosity is all the more precious and all the more urgent. Here's the thing about the Fermi Paradox that I keep coming back to. It doesn't just tell us about the universe, it tells us about our moment. We're living at the first moment in the history of our species when we're capable of systematically searching for other civilizations. We've had the basic physics for radio for about 150 years. We've had radio telescopes sensitive enough to pick up interstellar signals for about 65 years. We've been doing the search seriously for 65 years. That's less than a human lifetime. But the Milky Way is 13 billion years old. The 65 years during which we've been listening is about 0.0000005% of the galaxy's history. Not 0.5%, not 0.05%, half of 1/millionth of a percent. If you compress the entire history of the Milky Way into a year, we've been listening for about 0.002 seconds. And in those 0.002 seconds, we found nothing. And from that, we're supposed to draw conclusions about the entire history of life in the galaxy. The honest conclusion is, we can't. Not yet. The search is in its absolute infancy. We've barely begun. The silence so far is real, but it's the silence of a fraction of a second in a year-long story. What we can do with the silence is think carefully about what it might mean, plan the searches that would actually give us real answers, and keep the question alive. The Fermi Paradox is not a solved problem, it's an invitation to build better instruments, ask sharper questions, and be patient enough to hear an answer that might take decades or centuries to arrive. And while we wait, there's one thing we know for certain. We're here, right now, in this moment. curious and searching and alive in a universe that doesn't seem to be crowded with other curious, searching minds. Whether we're alone, or just early, or just not listening in the right way, that curiosity is ours, and the search is something we get to do. That seems like something worth continuing. The question the Fermi Paradox ultimately raises, and that we haven't yet answered, is this: if we are somehow the first or among the first, what responsibility does that place on us? What kind of answer do we owe to the universe's long silence? What would it mean to not just survive our technological adolescence, but to become the civilization that fills the sky with evidence of something real and lasting? While we have talked about the big picture of SETI, it is worth knowing what is actually happening at the telescopes right now, because the pace of change is faster than most people realize. The Meerkat radio telescope in South Africa consists of 64 individual radio dishes, each 13.5 meters across, roughly the height of a 4-story building, spread across an area about 8 kilometers wide. Working together, they function as a single instrument with the sensitivity of a dish, about 100 meters wide. Meerkat is one of the most sensitive radio telescopes in the world, and Breakthrough Listen has been conducting extensive SETI observations with it. The combination of sensitivity with modern signal processing lets researchers search for weak signals that would have been invisible to earlier instruments. In 2023, researchers from Breakthrough Listen and the University of Toronto published results from a machine learning search through about 150 terabytes of Meerkat data. They trained a neural network to distinguish between radio frequency interference from human technology and potential signals from space. The network identified about 20,000 candidates. After further analysis, 8 of those candidates were described as potentially interesting, appearing to come from the direction of nearby stars. They were not detected in follow-up observations, which is standard for SETI candidates. The signal appears once and then disappears. But the methods developed for that search are improving the entire field's ability to analyze data at scale. The Parkes radio telescope in Australia, with a dish 64 meters wide, about as wide as a Boeing 747 is long, has been part of Breakthrough Listen's Southern Hemisphere coverage. In 2021, researchers analyzing Parkes data found a signal briefly labeled BLC1 for Breakthrough Listen Candidate 1. It appeared to come from the direction of Proxima Centauri, our nearest stellar neighbor. The signal was at a frequency of 982 MHz, in a range that is relatively quiet for human-made interference. It drifted in frequency in a way consistent with a transmitter on a moving planet. For about a year, it was taken seriously as a candidate. Then careful analysis revealed it was almost certainly radio frequency interference from human technology on Earth. Likely electronics aboard aircraft or satellites that happen to produce a signal mimicking what an extraterrestrial source might look like. This happens frequently in SETI research. The universe is good at producing things that look artificial and are not, and Earth is full of artificial signals that contaminate the search. The disappointment of BLC1 is itself instructive. The fact that it could hold serious consideration for months shows both how carefully the work is being done and how hard the problem is. A genuine signal would need to pass every test that BLC1 failed. It would need to track consistently with a single source on the sky, not move like a satellite or aircraft. It would need to show the specific Doppler drift pattern of a planet orbiting a star. It would need to appear repeatedly across multiple observations. It would need to vanish when the telescope points elsewhere. Those are demanding criteria. Any signal that passes all of them would be very hard to explain as interference. The Square Kilometre Array, or SKA, being built across South Africa and Australia, will change the search entirely when it comes online. Its total collecting area will be about 1 square kilometre, roughly equivalent to 170 American football fields placed side by side. When complete, it will be the most sensitive radio telescope ever built, capable of detecting a signal equivalent to what an ordinary airport radar would produce at a distance of 50 light-years. That is the kind of sensitivity that starts making the search genuinely systematic rather than exploratory. Researchers in what is sometimes called SETI psychology have studied how humans might respond to confirmed detection of extraterrestrial intelligence. The findings are somewhat reassuring about our collective resilience. A 2020 analysis by researchers at the University of Edinburgh reviewed psychological and sociological research on how humans respond to discoveries that challenge their existing worldview. They concluded that people tend to be more resilient to worldview-challenging news than we expect. The history of scientific revolutions, from Copernicus removing Earth from the center of the universe to Darwin removing humans from the center of the story of life, shows that even deeply destabilizing ideas can be integrated into a culture's understanding over time without permanent social collapse. A specific study by Michael Varnum at Arizona State University exposed people to mock news articles about the discovery of microbial extraterrestrial life and measured their emotional reactions. The dominant emotion was positive. Curiosity and excitement outweighed fear and anxiety. When the hypothetical life was presented as microbial rather than intelligent, the positive response was even stronger. Simple life on another world seems to be something most people can hold with wonder rather than dread. Intelligent extraterrestrial life, and especially contact with it, is psychologically more complicated. The question of what they want, whether they are friendly or hostile, what their detection of us means for our safety, introduces uncertainties that might drive more anxiety. But even there, the research suggests that humans would likely adapt rather than break. We have a long history of encountering things that challenged our assumptions about our place in the universe, and we have generally kept going. What social scientists worry about most is the potential for coordinated misinformation in the period immediately following a detection announcement. Before any official characterization of a signal is complete, various groups with different agendas would be constructing competing narratives. The information environment around a first contact announcement could be chaotic in ways that previous announcements of major scientific discoveries were not, because social media and the speed of modern information flow did not exist during the Apollo program or the mapping of the human genome. This is not an argument against searching or against announcing a detection. It is an argument for thinking carefully about communication strategies before such an announcement becomes necessary. The scientific community has protocols. The question is whether those protocols, written before Twitter and before 24-hour news cycles, are adequate for a world that processes information the way we do now. Here is a reframing that helps put the Fermi Paradox in proportion. We have been thinking about it mostly in terms of space. Why do we not see signals from across the galaxy? But the more fundamental version is actually about time. The Milky Way has been producing stars for about 13 billion years. The first stars formed roughly 200 million years after the Big Bang, and were made almost entirely of hydrogen and helium without the heavier elements that chemistry requires. Those stars lived fast, died in supernovae, and seeded the galaxy with heavier elements. Each subsequent generation of stars enriched the galactic chemistry further. By about 9 to 10 billion years ago, roughly 4 billion years before Earth formed, the galaxy had enough heavy elements in some regions to potentially support rocky planets with complex chemistry. If life arises wherever conditions permit, and if intelligence develops on a timescale similar to Earth's, there could have been civilizations in the Milky Way that were already billions of years old by the time our planet existed. A civilization with a 4 billion year head start on us is not just more advanced in the way a 22nd century civilization would be more advanced than a 21st century one. It is more advanced in a way that is genuinely difficult to imagine. 4 billion years ago on Earth, the most complex life was single-celled. The entire history of multicellular life, of plants, animals, land colonization, dinosaurs, mammals, and humans, fits within the last 600 million years. Imagine a civilization that has been doing the equivalent of all that biological change, but technologically for 4 billion years. What does a 4 billion-year-old civilization look like? It might not look like anything we would recognize as a civilization. It might look like natural phenomena we have no framework to identify as artificial. It might operate at scales or using mechanisms we have not yet understood. It might be so different from us that our concept of civilization does not even apply. This is the part of the Fermi Paradox that truly resists easy answers. We are searching for things that look like us because that is all we know how to look for. But a civilization billions of years old might have undergone transformations so fundamental that the category of civilization has ceased to describe it. We might be surrounded by the consequences of advanced intelligence without being able to recognize them. The same way a bacterium in a city has no way of understanding what a city is. Let us spend time on a scenario that gets underappreciated. What if we spend the next 50 years comprehensively searching the observable universe for techno-signatures and biosignatures and find nothing? We would have to be careful about conclusions. Absence of evidence is not evidence of absence, but in science, comprehensive absence of evidence does become meaningful at some point. If we survey every nearby star for atmospheric biosignatures with instruments like James Webb and its successors and find none, that tells us that life with an oxygen-rich atmosphere is rare within several hundred light-years of Earth. That is a meaningful constraint. If we build the Square Kilometre Array and its successors and comprehensively survey the entire Milky Way at radio frequencies sensitive enough to detect a civilization like ours and find nothing, that would be significant. It would tell us that no civilization in the Milky Way is currently broadcasting in the radio band at power levels comparable to ours. That is not the same as saying no civilizations exist, but it is the most powerful statement we could currently make. If we find nothing in our solar system, nothing in nearby exoplanet atmospheres, nothing in galactic radio surveys, and if direct exploration of the nearest star systems finds nothing, then the most straightforward conclusion would be that life is genuinely rare. Not absolutely rare. There might still be civilizations in distant galaxies, but rare enough that our nearest neighbors are probably lifeless. This would be deeply informative. It would tell us that the Great Filter is most likely in the early stages, the origin of life, or the development of complex cells. And that would mean that we, as a technological civilization, are genuinely uncommon. The accident of intelligence arising here, on this planet, around this star, in this arm of this galaxy, would be an event of real significance. Not because we declared it so, but because the evidence would indicate it is true. There is a particular weight to this possibility. It transforms the often heard phrase that you are special from empty encouragement into something defensible by evidence. If we are alone or nearly alone, then the continuation of this curious, creative, deeply imperfect species becomes one of the most important things happening anywhere in the physical universe. Not because we deserve it, but because nothing else is here to do it. The Fermi Paradox is not just an astronomical question, it is a mirror. When we look at the question of why we have not found other civilizations, we are really asking, what happens to civilizations? And that question is directly relevant to ours. If civilizations routinely get to our stage and then fail, the failures are probably not random. They are probably caused by specific things. The development of powerful technologies without the wisdom to manage them. The tragedy of the commons applied to planetary systems. The inability to coordinate globally in the face of threats that require global coordination. The concentration of power in ways that prevent the distributed problem solving that allows complex societies to adapt. All of those failure modes are observable in ourselves right now, not as certainties but as tendencies. We have been managing nuclear weapons for 80 years without a catastrophic accident, but the risk has not gone to zero. We struggle to coordinate on climate change in ways that reflect the difficulty of global governance. Emerging technologies develop faster than the institutions meant to govern them. Power concentrates in ways that worry people who study political stability. None of this means we are doomed. History has examples of civilizations facing what seemed like insurmountable challenges and finding ways through. The 20th century produced 2 world wars and a Cold War that came close to nuclear exchange several times, and we are still here. The ozone layer was being destroyed and we fixed it. Smallpox was one of the deadliest diseases in human history, and we eradicated it. What the Fermi Paradox adds to this is a kind of statistical context. If civilizations typically solve these problems, the galaxy should be full of them. If the galaxy is quiet, maybe they do not typically solve them. Maybe we are playing a harder game than we think. This does not lead to despair. It leads to a kind of seriousness. The seriousness of understanding that what we are doing right now, collectively, as a species, in terms of how we manage our most powerful technologies and our most critical global challenges, might actually determine whether we become the kind of civilization that adds its signal to the universe, rather than quietly disappearing into the background. The Fermi Paradox asks where everybody is. One possible answer, the one that matters most practically, is they did not make it this far, and the question that follows from that is whether we will. Let us build the probability case for alien life from scratch, carefully, with honest numbers, because the case is stronger than most people realize, and the silence is therefore stranger than it appears. We start with the number of stars in the observable universe. The observable universe contains roughly 2 trillion galaxies. That number, 2 trillion, is 2 million millions. If each galaxy were a second of time, 2 trillion galaxies would be about 63,000 years. The average galaxy has somewhere around 100 billion stars. Multiply 2 trillion galaxies by 100 billion stars each, and you get around 200 sextillion stars. A sextillion is a million trillion, or a 1 followed by 21 zeros. That is 200 sextillion stars. Of those stars, we now have good evidence that at least half have planets, and of the planets, at least 10 to 20% are in the habitable zone. So we are talking about a minimum of about 10 sextillion potentially habitable worlds in the observable universe. That is the order of magnitude we are dealing with when we ask whether life is common. Now here is where it gets important to be precise. The question of how likely life is to arise given the right conditions is genuinely unknown, but we can bound it. If the probability of life arising on any given habitable world over its lifetime is as low as 1 in a billion, there would still be 10 trillion life-bearing worlds in the observable universe. That is 10 followed by 12 zeros, or roughly 1,300 times the number of stars in the Milky Way. Even at 1 in a trillion, there would be 10 billion worlds with life in the observable universe. These numbers make the silence in our immediate neighborhood somewhat less strange. Most of those life-bearing worlds might be too far away to detect. The observable universe extends 46 billion light-years in every direction. Most of it is genuinely inaccessible to our searches. We can meaningfully search only a fraction of our own galaxy, and even that fraction is barely scratched. But the numbers make the silence in the Milky Way harder to explain. If life is common, and if our galaxy contains hundreds of billions of stars, with billions of potentially habitable worlds, and if any small fraction of those worlds developed technology, there should be detectable civilizations here, in our own galaxy, not so far that the signal would have taken millions of years to arrive. Unless something specifically prevents those civilizations from becoming detectable. Which brings us back to the Great Filter. The numbers force us to take it seriously. Either life is genuinely very rare, rare enough that even in a galaxy with hundreds of billions of potentially habitable worlds, only a handful develop any form of life, and almost none develop technology, or something happens to technological civilizations that prevents them from remaining detectable for long. The math does not allow a comfortable middle ground where life is common and we are simply unlucky not to have found it yet. We mentioned the wow signal earlier, but it deserves more time because it is the closest thing we have ever had to a genuine candidate, and the story of how it was found and why it remains unexplained tells us something important about the nature of the search. It was August 15th, 1977. Jerry Amon, a volunteer researcher for the SETI program at Ohio State University, was going through printouts of data from the Big Ear radio telescope. Big Ear worked by printing numbers and letters to represent signal strength on a scale from 0 to Z, where a blank space meant nothing. Numbers 1 through 9 meant increasing signal strength, and letters from A upward meant even stronger signals. Normal background noise produced mostly 1S and 2S. A strong artificial signal might produce letters. On that printout, Amon encountered a sequence that read 6E=J5. The number 6 represents a signal about 6 times stronger than background noise, then E, which represents a signal 14 times stronger, then Q, 26 times stronger, then U, 30 times stronger, then J, 19 times stronger, then 5 times stronger. The peak of the signal, at U, was the strongest candidate signal Big Ear had ever detected. It lasted exactly 72 seconds, the time it takes Big Ear to scan across a fixed point in the sky. Amon circled the sequence in red pen and wrote "Wow" in the margin. The signal had several properties consistent with a genuine extraterrestrial transmission. It was at 1420 MHz, the hydrogen line frequency that SETI researchers had predicted would be the most logical channel for interstellar communication. It appeared to come from a fixed point in the sky, near the constellation Sagittarius, not from a moving source like a satellite or aircraft. Its shape, rising and falling as Big Ear's beam swept across it, matched what a point source on the celestial sphere should look like. Researchers pointed Big Ear at the same region of sky repeatedly over the following years and months. They found nothing. Dozens of subsequent searches with more sensitive instruments have pointed at that region and found nothing. The signal has never been observed again. Various explanations have been proposed over the decades. In 2017, astronomer Antonio Paris proposed that the signal was caused by hydrogen clouds surrounding one of 2 comets that were passing through that region of sky at the time. The comet hypothesis generated significant coverage, but subsequent analysis by other researchers identified problems with it. The comets in question do not appear to have been in exactly the right location, and the characteristics of the signal do not quite match what a comet cloud would produce. The WOW signal remains officially unexplained. It might have been a natural astrophysical phenomenon we do not yet understand. It might have been human-made interference from a source that has never been identified. It might have been exactly what it appeared to be, an artificial signal from somewhere in the direction of Sagittarius. We genuinely do not know. What we know is this. In 47 years of searching since 1977, including decades with instruments many times more sensitive than Big Ear, we have not found anything comparable. The WOW signal was an outlier in its own time. It remains an outlier. Whatever it was not the beginning of a flood of detections. The silence that followed it is part of the same silence that preceded it. To understand why the Fermi Paradox is genuinely puzzling, we need to understand how life arises and how hard that process might be. Because if the origin of life is easy, the great filter must be somewhere else. And if it is hard, the silence might simply reflect genuine rarity. Life on Earth arose roughly 3.8 billion years ago, possibly earlier. The earliest definitive evidence of life comes from ancient rocks in Western Australia called the Pilbara Craton, which contains stromatolites, layered structures built by microbial mats, dating to about 3.5 billion years ago. More controversial evidence for life, carbon isotope ratios in ancient minerals, suggests life might have existed as early as 4.1 billion years ago, only a few hundred million years after Earth formed. The fact that life appeared relatively quickly after Earth formed and cooled has been interpreted in 2 opposite ways. One interpretation says life arises easily wherever conditions permit, and the quick appearance on Earth reflects this. Another interpretation uses the anthropic principle. We necessarily observe a world where life arose early enough to produce us, so the quick appearance does not tell us much about the underlying probability. The actual chemical process that produced the first self-replicating molecules remains one of the deepest unsolved problems in science. We understand certain aspects of it well. We know that amino acids, the building blocks of proteins, can form spontaneously from simple chemistry. The Miller-Urey experiment in 1953 showed that when you apply electrical sparks to a mixture of water, methane, ammonia, and hydrogen, simulating what was thought to be the early Earth's atmosphere, you produce amino acids within days. Amino acids have been found in meteorites, including the Murchison meteorite that fell in Australia in 1969, which contains dozens of different amino acids not commonly found on Earth, suggesting this chemistry happens spontaneously throughout the universe. But getting from amino acids to self-replicating molecules is a much larger jump. DNA, which stores genetic information, cannot replicate without proteins. Proteins cannot be made without DNA. This chicken and egg problem is one of the central puzzles of origin of life research. The leading current hypothesis involves RNA, which can both store information and catalyze chemical reactions, suggesting that an early RNA world might have preceded the DNA protein world we have today. But demonstrating this in the lab remains challenging. The RNA world hypothesis requires RNA molecules to form spontaneously, to begin self-replicating, and to do so in an environment that allows natural selection to operate. Researchers have made progress on each of these steps separately. Assembling them into a coherent, continuous pathway from simple chemistry to self-replicating life is still a work in progress. What this tells us about the Fermi Paradox is, we do not yet know how hard the origin of life is. We have one example. The chemistry seems to go part way relatively easily. Whether it goes all the way easily, or whether it requires genuinely improbable steps, is not yet established. The answer to that question, if we can find it either through laboratory synthesis of life from scratch or through the discovery of life elsewhere, would dramatically sharpen our understanding of where in the chain the great filter sits. Astrobiology, the scientific study of the origin, evolution, and distribution of life in the universe, is a relatively new field with an unusual structure. It is studying a phenomenon, extraterrestrial life, that has not yet been confirmed to exist. It is trying to understand the distribution of something for which we have one data point, life on Earth. Despite this, the field has made genuine progress in the last 30 years. The discovery of extremophiles, organisms that thrive in conditions once thought incompatible with life, has dramatically expanded our sense of the range of environments where life could exist. Thermophilic bacteria that live in near boiling water around hydrothermal vents. Psychrophilic bacteria that are metabolically active in ice at temperatures of -40 degrees Celsius, cold enough that unprotected metal would become brittle. Radiation-resistant organisms like Deinococcus radiodurans, which can survive radiation doses several thousand times what would kill a human, a dose that would be roughly equivalent to surviving hundreds of simultaneous chest X-rays without any damage. These discoveries do not tell us that life exists elsewhere. They tell us that life, once it arises, is remarkably adaptable and can persist in a much wider range of conditions than we once thought. The search for life in extreme environments here on Earth has expanded our map of where to look elsewhere. The astrobiological assessment of Mars has become much more sophisticated. We now know Mars had liquid water on its surface for at least hundreds of millions of years during its early history. We know it had a thicker atmosphere and a warmer climate. Some regions of Mars, particularly around ancient lake beds and hydrothermal systems, might have been habitable by Earth-like microbes for long enough for life to have developed. The question is whether it did. The development of life requires not just liquid water, but also chemical energy, organic molecules and minerals, that can serve as catalysts. Mars appears to have had all of these. The ancient lake beds that Perseverance is exploring were almost certainly habitable. The question is whether habitable means inhabited. The answer to that question might be the most important scientific answer of the 21st century, and we might have it within a decade or two, when the Mars samples reach Earth and are analysed with the full power of Earth-based laboratories. If those samples contain clear biosignatures, the field of astrobiology transforms overnight from a discipline studying a phenomenon that might not exist to a discipline studying a phenomenon that is clearly widespread. If they contain nothing, the field learns something important about the rarity of life and adjusts its expectations accordingly. Either result changes what we think we know, and either result brings us closer to understanding the silence. One thing that rarely gets discussed in popular treatments of the Fermi Paradox is why the search has been so underfunded relative to its potential importance. Because if there is a question with higher stakes than whether we are alone in the universe, it is hard to name it. The total amount spent on SETI since the field began in 1960 is difficult to calculate precisely, but estimates suggest it is somewhere in the range of $100 to $200 million in total, cumulative, over more than 6 decades. The Breakthrough Listen initiative, with its $100 million pledge over 10 years, is the largest single investment the field has ever seen. For comparison, the United States spends roughly $800 billion per year on its military. The annual budget for SETI activities is a rounding error on the rounding error of the defense budget. Why is this? The answer involves a combination of politics, institutional priorities, and the way science funding tends to work. In 1993, NASA had a SETI program that was cancelled by Congress 1 year after it began. Senator Richard Bryan of Nevada, who led the effort to cancel it, described it as the Great Martian Chase and argued it was a waste of taxpayer money. The cancel happened after $12 million had been spent, about 1/60th of what the Breakthrough Listen initiative has now committed. The political economy of SETI funding reflects a broader pattern. Science funding tends to go to research that has a plausible near-term payoff, either commercially or in terms of national security. The search for extraterrestrial intelligence has no obvious commercial application and no obvious national security application. It is pure science in the oldest sense, driven entirely by curiosity about our place in the universe. In a funding environment that rewards applicability, that is a difficult case to make. There is also a sociological factor within science itself. For decades, SETI was considered slightly disreputable, associated in the public mind with UFO culture and science fiction. Serious astronomers were sometimes reluctant to be associated with it, even though the underlying science, radio astronomy, and signal detection is rigorous. That perception has improved substantially in recent years as the discovery of exoplanets has made the search for life elsewhere more mainstream. But the funding gap persists. The private funding model that Breakthrough Listen uses, relying on a single major donor rather than government funding, raises its own questions about sustainability. The initiative has produced real scientific results and improved the field's capabilities substantially, but it depends on the continued interest and funding of a small number of wealthy individuals. That is not a stable long-term model for what might be the most important search humans have ever conducted. There is a reasonable argument that the search for extraterrestrial life deserves a level of public funding commensurate with its potential significance. If the discovery of microbial life on Mars would be the most important scientific finding in history, the missions designed to make that discovery should be among the best funded in science. If the detection of an artificial signal from a distant star would transform our understanding of our place in the universe, the instruments designed to make that detection should receive the kind of sustained support that can only come from stable public funding. This is not currently the case, and the gap between the potential importance of the search and its actual funding is one of the stranger facts about how human civilization currently operates. Here is the variable in the Drake equation that might matter most, and that is hardest to estimate: the average lifespan of a technological civilization. Drake called it L, and he was talking specifically about how long a civilization sends detectable signals. But the broader question is how long technological civilizations exist at all. We have been a technological civilization, in the sense of using radio, for about 150 years. If you are generous and count the Industrial Revolution as the beginning of technology, it is about 250 years. Either way, we are extremely young as a technological civilization. We have no idea if our civilization will last 500 more years, 50,000 more years, or 5 billion more years. The answer to that question matters enormously for the Fermi Paradox. Here is why. If the average technological civilization lasts 1,000 years, and if they form at a rate of 1 per year in the Milky Way across the galaxy's history, then at any given moment there are only about 1,000 technological civilizations active simultaneously. In a galaxy of 400 billion stars, 1,000 civilizations is one civilization per 400 million stars. The average distance between them would be enormous, roughly 24,000 light-years by some calculations. At that spacing, communication by radio is possible in principle but extremely slow, and the chance that any two civilizations would be close enough to easily detect each other is small. If civilizations last 1 million years on average, the calculation changes completely. At that lifespan, there would be 1 million active civilizations simultaneously, and the average spacing drops to something like 250 light-years. That is close enough that civilization should be filling the galaxy with detectable signals. So either civilizations are very short-lived, lasting only thousands of years, or they do not arise as frequently as simple Drake equation estimates suggest, or something else stops them from filling the galaxy with signals. All three of those options have uncomfortable implications. Short-lived civilizations are a warning. Rare civilizations point to a hard, great filter. The third option, something stopping signals from spreading, requires explaining what that something is. The history of civilizations on Earth, though none of them were technological in the modern sense, is not encouraging about longevity. Complex societies have repeatedly collapsed under the pressure of environmental degradation, overextension, internal conflict, and the failure of governing institutions to adapt to changing circumstances. The Roman Empire, which administered millions of people across Europe, North Africa, and the Middle East, collapsed in the West within a few centuries of reaching its peak. The Maya civilization, which developed sophisticated mathematics and astronomy, collapsed dramatically around 900 CE. The Bronze Age collapse around 1200 BCE saw the simultaneous collapse of virtually every complex society around the Mediterranean. None of these were technological civilizations in the modern sense. They lacked nuclear weapons, engineered pathogens, and artificial intelligence. Their collapse did not threaten the species, but the pattern of collapse is real, and it suggests that complex civilizations carry within them the seeds of their own disruption. Whether that pattern continues for technological civilizations is one of the most important questions we can ask. Let us get specific about what the next decade of observation will give us the ability to detect and what conclusions we might draw. James Webb Space Telescope is already in operation and producing exoplanet atmospheric data. Its infrared sensitivity allows it to detect the spectral signatures of specific molecules in the atmospheres of planets orbiting nearby stars. The molecules of most interest for biosignatures are the ones that would be out of chemical equilibrium without a biological source. Oxygen is the primary example. Methane alongside oxygen is particularly interesting because oxygen and methane react with each other and cannot coexist for long without something continuously replenishing both. On Earth, oxygen is replenished by photosynthesis and methane by microbial metabolism. Finding both together on another world would be a strong biosignature. James Webb has already detected water vapor, carbon dioxide, sulfur dioxide, and methane in various exoplanet atmospheres. The K218b detection of possible dimethyl sulfide generated significant attention. Follow-up observations are ongoing. The challenge is that K218b is a sub-Neptune planet with unusual characteristics, and models of its atmospheric chemistry are not certain enough to definitively claim a biosignature. What the detection shows is that the capability to make these measurements exists. We are doing the search in earnest. The Nancy Grace Roman Space Telescope, scheduled to launch in the late 2020s, will survey large areas of sky with high precision and will be capable of detecting thousands of new exoplanets through a technique called gravitational microlensing. It will not characterize their atmospheres directly, but it will dramatically expand the catalogue of known planets and improve our statistical understanding of how common various types of planets are. The Habitable Worlds Observatory, currently in the conceptual development stage at NASA, is designed specifically to directly image Earth-like planets around nearby stars and analyze their atmospheres. Direct imaging is harder than transit spectroscopy because you need to separate the extremely faint light of the planet from the overwhelming glare of its star. The planet is typically about 10 billion times fainter than its star when viewed in visible light, roughly the same ratio as a firefly next to a lighthouse from a distance of 100 miles. The Habitable Worlds Observatory would use a combination of large aperture and specialized coronagraphs, instruments that block the central star's light, to make this possible. If that telescope is built and operates as designed, we will have the capability to characterize the atmospheres of dozens of Earth-like planets within about 30 light-years of Earth. Those 30 light-years contain about 300 stars. Within those stars, there might be several rocky planets in habitable zones with atmospheres we can analyze. If any of them show robust biosignatures, we will know. This is not a distant aspiration. It is a specific technical plan with a plausible implementation timeline. The combination of these observations, Mars sample return, exoplanet atmosphere characterization, continued SETI radio searches with improving instruments, and ocean world missions will give us by the middle of this century an empirical basis for the Drake equation that we simply do not have today. We will know whether simple life is common or rare in our solar neighborhood. We might know whether Mars once harbored life. We will have characterized dozens of exoplanet atmospheres. We will have surveyed the Milky Way at radio frequencies with unprecedented sensitivity. Whatever the results, they will tell us something profound about our situation. The silence might persist and deepen our understanding of why it exists, or it might end. Either way, we will know more, and knowing more is what the search has always been about. Here is something I keep returning to when thinking about the Fermi Paradox. The question is not just about them, it is about us. When we ask why we have not found other civilizations, we are implicitly asking what kind of thing we are. Are we the first? Are we the survivors of something that most do not survive? Are we a temporary phenomenon that the universe briefly produces and then reclaims? Are we one small outpost of intelligence in a vast sea of biology that never quite made it to technology? Are we surrounded by minds so advanced they have moved beyond anything we would recognize? Each of those possibilities says something different about what it means to be here, doing what we are doing in this moment, and each of them implies something different about what we should be doing with the time we have. If we are first, we are pioneers. We are the first voice in a universe that will eventually be full of voices, if the things that came after us survive long enough to add their own. Being first means the universe is watching what we do, not with intention, but in the sense that what we do will echo forward through cosmic time. The civilizations that arise after us, if they come into contact with our legacy, will learn what kind of thing intelligence was at its earliest stages. If we are survivors, we are extraordinarily lucky. We made it through something that most do not, and understanding what that something is Whether it was the origin of life, or the development of cells, or the transition to multicellularity, or some combination, matters enormously. Because if we know what the filter was, we can understand how close we came to not existing. If we are temporary, the question becomes how to use the time well. Not in a frantic way, but in the way that any conscious being who understands their finitude has always faced. What matters? What lasts? What is worth doing in the window we have? If we are surrounded by advanced minds who have transcended our ability to detect, then the universe is even stranger than we think, and the path forward involves not just improving our instruments, but improving our imagination about what we are looking for. None of these is a reason to stop searching. All of them are reasons to keep going. The search for life in the universe is the most human thing we have ever done. Not because life is certainly out there, but because the question is worth asking, the tools are getting better, and the answer, when it comes, will be one of the most important things humanity has ever learned. The silence continues. We keep listening. That seems exactly right.